So my question was, what does a sub n plus 3 have to do with a sub n plus 4? In other words, is it before, is it after? How many before, how many after, Jack?
It is the term directly prior it.
It is the term directly prior, so it's one term before. One term before.
Well, if I was paying attention.
What was that?
I said 3 after.
So did
Because I thought it was 1.
And absolutely it would be 3 after if I gave you a sub n, but you have to be very careful about what we start with. I gave you a sub n plus 4. This is definitely 1 less. If you struggle with seeing that, just put a number in. Put a 5 in for that n. Well, that would be 5 plus 4 would be the 9th term, and this would have been the 8th term. That's 1 term before. Well, if n plus 3 is 1 term before, what is a sub n plus 2 then? It's going to be 2 terms before. 2 before. So if I give you the 10th term, you're going to give me out the 8th term based upon that. And if you have them all listed, sometimes it's nice to be able to go, okay, this term, I'm looking for the 1, 2 before it, and then you find that number. All right, we're supposed to write 2 formulas for 7, 10, 13, 16. First of all, it is arithmetic because we can add 3 over and over and over and over and over and over and over. Actually, we stop. We stop at 16. I'm just going to go ahead and take a picture since everyone did get it correct. And that way we don't have to go through it. But I said, hey, it is arithmetic. Whenever I know something's arithmetic, I'm going to go ahead and say my first term is 7. And my common difference is 3. With my recursive, look at your recursive state right now. Do you have a sub 1 equals 7 under your recursive formula? Okay. Yes, that's good too. Nice. I was thinking about if you wrote recursive and then you wrote a sub. But as long as you have it right next to it, then you can get all the points. You're missing this, you're missing a point. My explicit one was a sub n equals our difference, which is 3, plus 4. Remember that 4 is our c value? Our c value is our first term minus our difference. Well, our first term was 7 minus 3, which gave me that 4. No. What's up?
Do we need to write like recursive and explicit on like which one's which?
No, I can figure it out, but it's always nice to keep things organized. I noticed when I did this at first, I didn't have the recursive, I didn't have the explicit, so I just quickly wrote it in case I'd show this picture. Then you'd have recursive spelt wrong because there's no e, and that v is a little weird there. No, you definitely don't have to. I know, and you better know. All right, questions on this? On this? Okay, questions on the homework. Questions on something else. What was your question?
Does your new case have like a different kind of like slot for your hand? It looks like it's different. The other one was like flat, and now it looks like.
Yeah, it's different. Yeah. It's also bluer. Gabby, did you have a question?
I did, yeah. Can you go through 12?
Oh, the case thing didn't answer your question. Yes, I'll go through 12. Number 12? Am I looking at the wrong sheet? Oh, I'm looking at today's homework. That's why there's no 12. I'm just like, I didn't assign 12. So 12 is writing the first 5 terms. Am I on the right assignment?
Yes.
Okay. Writing the first 5 terms of the arithmetic sequence, given that our first term is 72. So this is going to be number 12. It says my first term equals 72. And it also says my recursive formula is a sub n equals a sub n minus 1 minus 6. So my first 5 terms. Do I do anything else? Write the first 5 terms, find the common difference, and write the nth term. Oh, we're supposed to write an explicit formula on top of that. All right, so my first term is a sub 1 equals 72. So a sub 2 is going to be, well, this says a sub n equals the term before it minus 6. We're just going to take the term before it, which is 72, and subtract 6 from it. which is going to equal 66. And then we do the same thing for the third one, so that would be 66 minus 6 equals 60. A sub 4 would equal 60 minus 6, which would be 54. And finally, my A sub 5 would be 54 minus 6, which would be 48. Well, the good thing about this equation here, if it asks for your common difference, in recursive land, that negative 6 must be my common difference. So that negative 6 is my common difference if we're in recursive land, not explicit land. We'd like to say the term before or something. So my D equals negative 6, and my first term is 72. So that means my equation is going to be A sub n equals my common difference, negative 6, n, plus, and what goes here is my A sub 1 minus my D value, and maybe I should actually put minus my D value, which in this case my A sub 1 is 72. So that's 72 minus that negative 6, which is going to give me 78. So it's plus 78. Is that good?
Yeah.
I just saw you working on the one above
Yeah,
it. So I think
that's-
whatever I said clicked. Yes.
Can we go over 8?
8, but that's before 11.
Sorry.
You should put your hand up faster. No. Okay. So number 8. Number 8 gives us. Let's open up a blank slide. Number 8 just gives me that it is arithmetic, and that my 5th term equals 190, and that my 10th term equals 115. I need to go ahead and get that common difference. I need to get that common difference. And to get that, I'm going to say, well, A sub 5 plus, and I'm going to count how many steps it takes to get from 5 to 10, and that's 5 steps. It's just 10 minus 5. So plus adding D 5 times is going to get me to my 10th term. Do you all agree with that? These can be tough. But it's basically I'm just adding D to get to 6, D to get to 7, D to get to 8, 9, 10. So that's 5 individual Ds that I'm adding. Well, let's put in the totals. Well, this is going to be 190 plus 5D equals not AD. It's going to equal 115. And we should come up with D equals a negative 15 if you do all this right. Now we need to get that first term because I need my difference and I need my first term. To get to the first term, it's pretty low. You could just do 190 minus 15 minus 15 minus 15 minus 15 until you get to 1. Or you can set up another equation that says A sub 1 plus, well, to get to 5, I have to add 4 D values to equal my 5th term. Once again, we fill in the information I know. So I have A sub 1 plus 4 times, this time I do know the D value, which is negative 15. And that's got to equal my 5th term, which is going to be 190. You solve all that. Let me make sure everything is correct so I'm not leaning down the wrong path. That should equal 250. Yeah, because 4 times 5 would be 40, 60. Yep, 250. And that's my first term and my difference. Do you need me to go further or is that good? All right, awesome. Other questions? Yeah. 14. 14 gives me, it's asking for the 8th term. They do give me, because they're really nice, they give me the first term, and they give me the second term. What they're actually asking me for is an explicit formula, so I can just plug 8 into it so I can get that value. So our goal is to come up with an explicit formula. Knowing it is arithmetic, in order to come up with an explicit formula, I need to have the first term, got it, and I need to get the second difference. I don't have that yet. I need that difference. Well, to get that difference, I just got to figure out how do I get from here to here. In other words, this plus what gives me that. So we can just do negative 13.8 minus this negative 0.7. In other words, our difference is going to be negative 13.1. Because if I have 0.7 subtracting negative 13.1 equals negative 13.8. Then it's just coming up with our explicit formula. Would you like to see that, or are you okay from here?
I think I saw it.
You started it wrong?
No, I think I saw what I did wrong.
Oh, okay.
Can you keep going though? Why wouldn't you be able to just do like negative 13.1 times 8 to get the 8th term?
Well, that would be starting at 0.
Oh yeah, you need
That would be starting at 0. I am starting here. So you could do...
And subtract 0.7?
Yeah.
Or add it.
Yeah. You could. In other words, what we're actually asking you to do is come up with a formula. I'd probably say come up with a formula and then find that value. So you should come up with a formula. That way you can just plug it in.
Alright, can we go over that?
Yeah. I'll take a picture of it. Oh, I didn't even do it. Then I will not take a picture.
That means we'll have all the credits for the homework assignment.
I have the answer on it. I just don't have the work down for it.
So if you get it wrong, I can't give you full point.
Is this true? All right. A sub n is going to equal my common difference, which is negative 13.1n, plus that c value. Remember, our c value is the first term. Let me erase that. Well, we'll just leave that as so it'll be my first term minus my difference. My difference is negative 13.1. So you have to be really careful about your negative signs here because it's minus a negative. So it's actually we're adding.
So 12.4.
It's going to be 12.4. And now I can just plug an 8 in for that n, and I'll get that value out a little quicker. But you could, like you were saying, what you're basically doing is you're taking negative 0.7 and just adding negative 13.1 until you get to your 8th term, which will work. In a clutch situation, it'll work. But, I mean, if I ask for the 92nd term, you probably don't want to keep adding it. And you probably don't want to make a little mistake by going, 92 times this. And what am I subtracting? What am I adding to it then? All right. Is that good?
Yes.
Okay, awesome. Other questions? All right. Then we will go on to series. I actually have to go back a slide. I messed up these slides to be nice. But I'm going to talk about series real quick. A series is just an indicated sum of all the terms of a sequence. So we've come up with sequences. What a series is actually adding each of those elements together. Well, a series has two different types. It's not really crazy. It's the same thing we did with sequences. A series can be finite. An example of a finite series might be 1 plus 2 plus 3 plus 4. These are nice because you can come up with a nice total. Well, that's 5 plus 5 is 10. That's a finite series. It has a beginning. It has an end. We also have infinite series and beyond. This could start out the same way and look almost identical, except for we aren't going to stop. We're going to go dot, dot, dot. And it's going to keep going on forever, infinitely, if you will. And beyond. To infinity and beyond. All right. Not really mind-blowing.
I'm waiting until the day where you say it's bigger, it's better.
It's all right. Sigma notation. Sigma notation in mathematics tells you are doing a series. You're doing a sum of things over and over and over. So the Greek letter sigma, shown above, that's a little E-looking thing, is just shorthand for a series. And this is the shorthand version of a series. And let's write down what this means. All right? The 1's important, the 6 is important, the 3K is important. Okay. This, what we have right up here, is shorthand for the following. It is plugging 1 in for that K, so we have 3 times 1. Then we're going to add 3 times 2. Then we're going to add 3 times 3. Then we're going to add 3 times 4. Then we're going to add 3 times 5. And why not just do 3 times 6?
So K is the difference.
K is the one that's changing every single time, and it's changing based upon this 1 and 6. This 1 and 6 is actually count from 1 to 6 and replace your K values with those values. So I replace it with 1, 2, 3, 4, 5, 6, and as soon as I get to the 6, I'm done. Now, we're not going to, but you would add all these up, and you'd get your total.
Can we have that?
You sure can, and have fun with it. All right. The symbol 3K is called our summand. That is right here. We don't usually use that term. I will probably, that might be the only time you hear me say it. And the numbers 1 through 9, that is not true. I changed it so we didn't have to go to 9. This is actually 1 through 6. So at one point we're going to write all the way to 9, but why when you get the point 1 through 6? So 1 and 6 are called limits of your summation, which makes sense because that bottom one and that top 6, they tell you where to start and stop. That top number is not always a number. Sometimes it'll be that sideways 8 or an infinity sign. That just tells you it's an infinite series. It just keeps going on and on and on. The last thing we're going to talk about is our index. Our index is just the letter K in this example. It is just your letter. So this is our index. You can pick any variable you want to. You can make smiley faces. You could make rainbows. I don't care, as long as they're the same here as they are here. So as soon as you pick a letter here or something, it has to be the same on the other side. Traditionally, we use like I's and J's and K's. I'm not a big fan of using I's and J's. I will. I just find I's and J's blend together, and I don't like variables that you have to dot.
Can we use a tau?
Yes, you can if you want to. Generally, we don't use Greek symbols for placeholders like that, but if you want to, live it up.
What about XE?
No, you can't use that. Okay. Write the following in an expanded form. Once again, that 1 and 4 are our limits. We're going to start at 1, and we are going to end at 4 by plugging those values in for that n. So this is going to be 1 squared plus 2 squared plus 3 squared, and finally plus 4 squared. And this is going to come out to 30. Now this is, it's not super special, but we have a name for this because it has a beginning and an end. This is called a partial sum. It's called a partial sum because I'm taking part of it out, because technically we could go on forever. I could go the other direction with it, or I could do 5 squared, 6 squared, 7 squared, 8 squared. So I'm taking a part of it and just finding the sum of it. What is it from 1 to 4? The next one you can see goes from 1 to infinity. So it's the same problem, except now it goes to infinity. So this one would be something like 1 squared plus 2 squared plus 3 squared. Ooh, that's not a 3. That like... That's why I had to change it. Plus goes on forever. This is called an infinite series, or you can call it an infinite sum. We technically only call it an infinite sum when you can actually add them together. There are cases, and we'll talk about it. What day is it? Tuesday, Wednesday, maybe Thursday. There are some of these that go on for infinity, but we can still actually come up with the sum of it. Then we talk about it as being an infinite sum because I can calculate it. This we can't calculate it because this is going to get bigger and bigger and bigger and bigger and bigger.
If it goes for infinity both ways, does that equal 0?
If I kept going the other direction?
Yeah, because each
Yes,
one
in theory, yes.
adds to 0. Wow.
In theory, yes. Infinity is a weird, fickle beast that we don't really talk about it that way, that they cancel each other. All right. Our next one, look at that I. Oh, mine are different than yours, right? I think I fixed your addition. Your variable's a little different, right?
Ours
we
is
have,
I.
yeah, ours are.
Yours is
Yeah, yours should be I and I, because I did say, so I put it on here to catch, but I decided to go back to the original. Yours should match. They should always match. If this is I, this is I's, and yours should match. This is
And if it doesn't match, it's no solution.
basically.
What if one is I and the other is you?
All right, anyway, So we are going to recognize that this actually starts at 3. So we are not going to plug 1 in this time. We're going to start at 3. So this is going to equal 2 times 3 minus 1 plus 2 times 4 minus 1 plus 2 times 5 minus 1 plus 2 times 6 minus 1. Maybe I'll put the numbers that I'm changing in parentheses just so they stand out a little bit more. So I counted from 3 to 6, including that in our I values. And this one should come out to, I got 32. Our last one's that weird one that you get to a test and it throws you for a loop. So make sure you pay attention to how to do one that looks just like this. It's not hard, but if you don't know what to do, it's one of those that puts you in a tailspin and makes you feel like you don't know what you're doing. Yes?
Can I take a guess?
You can totally take a guess.
You just do like 4 plus 4 plus 4 plus 4 plus 4 because there's no I value, so you don't have to add it up.
Absolutely. You're going to do 4 plus 4 plus 4 plus 4 plus 4 because I'm going to plug 1 in for my first thing. Well, there's no I for me to plug it in, so it doesn't change the 4. So this is going to equal 4 plus 4 plus 4 plus 4 plus 4. You're just going to be careful to make sure. So I'll put those I values above. 1, 2, 3, 4, 5. This is where I plug in 1. This is where I plug in 2. This is where I plug in 3. This is where I plug in 4. This is where I plug in 5. There's no place to plug it in. So the 4 stays the same. So in fact, this is just 4 times 5, or the old 20. The old 20. Oof. Questions? All right, let's step it up a little bit. Now we're going to go the opposite direction. We're going to now write a series. We are now going to write our series. In order to write a series, we first have to come up with an explicit formula. So our goal is to come up with an explicit formula, and we're going to use that to actually write our series. So this first one, you're going to not think about it as being 2 plus 4 plus 6 plus 8. What you're going to think about in your head is 2, 4, 6, 8. Who do we appreciate? 10. Well, we are going to add 2, add 2, add 2. So this is definitely arithmetic. It's arithmetic where a common difference equals 2. Now we're going to go ahead and write our explicit formula. Our explicit formula is going to equal our difference, which is 2, times n, plus that c value, which is our first term, minus our difference, which equals 0. Yep. That is our 2 minus 2. So our official explicit form is just a sub n equals 2n. Once you come up with your explicit, you can go ahead and write your series notation. When you do these on your own, if you look back here, you are allowed to start at 3, but do not make your life difficult. Always, if you're creating your own, whatever variable you pick, I'll pick n, always start as 1. Always start at 1. It just makes your life a lot easier. So I'll start at 1. I'll write my explicit formula, which would be 2n, and then I have to say where to stop. If I start at 1, I just got to count how many terms we have. We have 1, 2, 3, 4, 5, so I need to stop when I get to the 5th term. Yes?
So why is this all coming back? Because we did this in algebra 2.
Mm-hmm.
Pretty much the same.
Pretty much the same, yeah. It's kind of like Algebra 2.5 review of concepts, getting to more quicker, harder problems. Math always stacks on top of it. If you look at Algebra 2, it had a lot of Algebra 1 concepts in it.
It totally did.
The only oddball one is geometry. It kind of just floats out by itself, but the rest of them should be stacked on top of each other.
Like chickens.
Because when you get to calculus, it's a good question because when you get to calculus, you have to have this down cold. So when you get to calculus, they're not going to review it again. You're just going to jump right into series and how you can use it for calculus. So this is kind of your last chance to understand it and ask questions, because once you get to calculus, they're just going to assume you know it and move on. All right. Yes? That's a question. Okay. Hey, make sure you check your answer. So I say my first term should be 1 times 2, which would be 2. Yeah, 2 plus. Then our n becomes 2. 2 times 2 is 4. Yep, we're good. 3 is 6. And my last one would be 5 times 2, which would be 10. So all the numbers match up. All right, our next one's a little more difficult. It's a little more difficult because it is alternating. And you'll see I do this all the time. I like to throw these at you all the time before you become really good at it. It is alternating between positives and negatives, which means you are going to either use negative 1 to the nth power or negative 1 to the n plus 1 or n minus 1. I usually stick with n and n minus 1. Does anyone remember how I decide which one of those two to use? Yes?
If it starts positive, don't you do n minus 1 because you start with 1 and 0 negative for any whatever number, the 0th power is always 1.
Yep, perfect. So I look at my first term, it's positive. My first term is positive. So I'm going to plug a 1 in here. Well, negative 1 to the first power is negative. That doesn't give me my first term being positive, so that scratches out. If I plug a 1 in here, we have 1 minus 1 is 0. Negative 1 to the 0th power is positive, which would make my first term positive. So you're just going to choose between which one of those based upon what your first term is, plugging a 1 in. All right, as soon as we get rid of our positive and negative, then we're really just talking about 1 over 5, 1 over 7, 1 over 9, 1 over 11, and 1 over 13. So I already took care of our positive, negative, so we're on to just our pattern there. Well, this is actually an algebraic denominator. Look at the denominator. I have to add 2, add 2, add 2, add 2. So just the denominator is adding 2, is adding 2. And so in my denominator, my explicit form is going to be, my difference is 2. So we'll have 2n. Remember, it's just the denominator, so it's actually 5, 7, 9, 11, 13. Maybe I'll highlight that. We're just talking about a denominator. And so it's 2n plus my first term, which is 5, minus 2, which equals 3. Once again, that is my 5 minus 2 gives me my 3. That is what I want in the denominator. My numerator needs to stay a 1. So my completed statement is going to be negative 1 to the n minus 1 times 1 over 2n plus 3. So my series notation is going to be, let's change it to, let's change it to m. M equals 1. I'm going to move that negative 1 to the top. And I'll have 2m plus 3. I'm going to count how many terms I have. I have 1, 2, 3, 4, 5 terms. So we're going to go from m equals 1 till we get to m equals 5. And that is our formula.
It's 2n plus 3 at the bottom.
It is 2m plus 3 because I have to replace, that should be an m2 actually. They should all be m's because if I pick m here, the rest of them have to be m's as well. Okay, so my original one, I had n in for it. You could have just picked n. Makes it easy. I just wanted to switch it up to an m. For no rhyme or reason. So there's no, you have to switch it to m if you see this. It's whatever you want there. All right,
Bumblebee.
what was it? Yeah, you could. I'm going to skip the next one just for time. Just for time. If I have time, I'll come back to it. But I really want to get to changing the index. I want to get to changing the index. So changing the index is basically, so this is an arbitrary starting point. I just pick it as 2, and we go to 6. Sometimes when we start at 2, we actually need to start at 1 to match it up with something else. Some other series I want to match up how they react to each other. So for whatever reason, you may want to change that I equals 2 to an I equals 1. Well, instead of making it I equals 1, I want to change it to K equals 1. So the whole point of what we're doing right now is I want to be able to rewrite this thing as K equals 1 on the bottom. But I want the sum to stay the same. So everything needs to change in it to accommodate the fact that I'm taking a step back here. This is probably the easiest way to take care of it. There's multiple ways to think about it, but this is probably the easiest way, at least starting off thinking about it. So the first thing we're going to do is, well, if I have I equals 2, I want my K to equal I minus 1. Because I asked myself, how do I get from 2 to 1? And that is you just subtract 1 away from your I. So my I equal 2, 2 minus 1, that gives me my 1. Well, if I'm making K equal I minus 1 to give me that 1 over there, I can also rewrite this. I can rewrite the statement by adding 1 to both sides, that I must equal K plus 1. So I just added the 1 to both sides. Now that I know that I has to equal K plus 1, all you're going to do is you're going to take that value and plug it in for that I. And so this is going to equal K plus 1. And now that's 6. We have to change that 6. We have to change that 6 because I changed my index down 1 value. So I'm going to change my top limit down 1 as well. So that's going to be 1 through 5. Now, you don't have to do this fully, but I would at least double check really quick, just a couple values to make sure it is correct. We're going to do the whole thing to make sure both of these are the exact same. So my first one is I equals 2 to the 6 for I. Let's see what that sum equals. Well, when I place 2 in for that I, we'll have 2 plus 3 plus 4 plus 5 plus 6. Let's make sure that second one is the exact same. So the one I changed, we had K equals 1, and we said that's going to go to 5, and that's going to be K plus 1. Well, that's going to equal, I have to write pretty small to get it all to fit here. Well, we start with 1, so we'll have 1 plus 1, plus, now we move on to 2, so it'll be 2 plus 1. Then we move on to 3, which is 3 plus 1. Then we move on to 4, so we have 4 plus 1. And finally, we move on to 5, so I have 5 plus 1. Simplifying that, we'd have 2 plus 3 plus 4 plus 5 plus 6. It is the same exact equation. I just lowered my index by 1 value. That's just a check, and you should probably do at least a little bit of that. Yes?
If K equals 1, why wouldn't it be 1 plus 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 1?
Okay, well, K equals 1. So if I plug a 1 in here, we have 1 plus 1.
Yeah.
Then our next value would be 2. So I plug a 2 in for that K, that'd be 2 plus 1.
So K would equal 2 for this second.
The thing on the bottom is just the start.
This is my start, and this is my end. It's just like when we had back
So
over
the-
here.
The K on the bottom, the K switches value, changes value.
Just like any sum. Just like all the ones we did back here. Just like this one. My K switch values went from 1 to 2
Yeah.
to
I don't
3
know
to
why-
4 to 5 till we get to 6.
I don't know why that just started confusing me right now.
Nope, you just count 1 through, so this one just tells you, count 1 through 5, replacing all your K's with 1 through 5 values, and add that as values. All right, bottom left one. Bottom left one, I have I equals 3 to infinity, and we have 1 over I squared. Remember, the whole goal of this and our directions say we want to change our index to k, and we want k to equal 1. All you have to ask yourself is, how do I get from 3 to 1? And that is subtracting 2. So our k is going to equal I minus 2, because my I starts at 3, and if I subtract 2 from it, I get to 1. Well, if k equals I minus 2, then our I must equal, add 2 to both sides, and you have k plus 2. And all you have to do is replace that k plus 2 for that I. And so for this one, we're going to have 1 over k plus 2 squared. And since I went down 2, I went from 3 to 1, I went down 2, we actually have to have infinity minus 2. But I will never, ever write that a day in my life. I'm just going to put infinity, because infinity minus 2 is the exact same thing as infinity minus 3. It's the exact same thing as infinity minus infinity. It's still infinity. All right.
Infinity minus infinity, like 0?
No, it's infinity. Because tell me where to stop and where to start subtracting.
Oh.
That was mind-boggling.
All right, what I want you to do is I want you to do that last one. And while you work on that last one, I'm going to come around real quick and I'm going to check your homeworks. So have them out so I can check them really quick. Which one am I checking? But that will be enough. All right, I need to convert this to where we have k equals 1 on the bottom, which means I need to add 2 to my I value. So we're going to come up with k equals I plus 2. Well, based upon that, my I must equal, well, I subtract 2 on both sides, so we have k minus 2, and we're going to take that k minus 2 and replace it for both of our I values. So we are going to have negative 1 to the k minus 2, all over 2 times k minus 2 plus 1. And since we actually went up 2 values, went from negative 1 to 1, your 5 is going to change to a 7. So you should have a 7 on top. Then we should simplify. So on the bottom, I'd have 2k. 2 times negative 2 is negative 4, plus 1 is a negative 3. You can actually simplify this top. This is optional, but let me tell you what I just did real quick. I'm not worried about you actually doing it, so I put it as optional. The reason why you can do this, because if I if I put a 1 in for this k value on the top, I have 1 minus 2, which gives me negative 1, which is odd. Negative 1 times an odd number is going to be negative. If I come down here and plug a 1 in for this k, 1 is odd, so I also get a negative out. So in fact, negative 1 to the k is the exact same thing as negative 1 to the k minus 2. It'll just alternate between negatives and positives. Yeah?
If there's a negative, that's going to be inverse.
But we're dealing with negative 1.
That wouldn't change.
Yeah, it wouldn't change anything. In fact, negative 1 to the k would be the exact same thing as negative 1 to the k plus 2. It'd be the same thing as k plus 4, k plus 6. As long as it makes the first one negative, it is the same value. Yeah?
Wait, so negative 1 to the negative first power, isn't that like 1 over negative 1?
Yeah, but it's still going to be negative.
If it was anything more.
If it was anything else, if it was like 2 to the negative 2, then you have to worry about flipping it. But with 1, even though it's negative 1 over 1, it's still negative 1, which means it pulls a negative out front.
Okay.